Okay. The idea is that first of all you should be able to solve problems. If you solve all of the problems, to be precise, a sufficient amount of them during the written exam, if you do this correctly, then it will be enough. If not, then you will need to answer some additional questions, maybe solve additional problems. So the next hour part is needed only if you're not that good at solving problems. So, so this was like this during my university years. I'm doing the same. Since the most important is to be able to actually solve equations or compute Fourier transforms. Okay, so let us finish with the previous topic. And this subtopic, so the last subtopic is time-dependent boundary conditions. So, what we had originally, we had the wave equation which was defined either on the half line, this is t, this is x. So on this boundary of this domain in tx plane, we had u of 0 and x equals u0 of x, and ut of 0 and x was u1 of x. And here we had either u of 0, u of t and 0 was either this one was 0 or u x of t and 0 was 0, or some combination of them was 0. So it's a bit non-symmetric, because here we had arbitrary functions, and here we should be restricted by these conditions. So how to fix this? And also, so there was this situation. There is also a situation with two boundaries. T, this is again x. So here we have, let us look at the first case. So here we had u of t 0 equal to 0, and here we had u of t l equals to 0 again. So what to do to solve the general problem when we add arbitrary time dependence for this function? Let us call this ul of t, and here we have a left and right boundary condition. Here we have u right of t. When left stands for left, right, L stands for left, R stands for right. So on the first approach, which works in both cases, and maybe in the format, maybe it's the only approach which works here. Maybe not actually. So this approach is essentially to reduce this problem to the problem we know how to solve. Mm. Uh, so the idea of this approach is to transfer boundary conditions to the right-hand side. So to do this, we consider a new function. So u tilde of t and x equal to u of t and x minus ul of t minus 1 minus t over t 1 minus x over l u r of t. Sorry, not that simple. No. This one. So if you do like this, then this term vanishes at 0, and this term is equal to ul of t at 0. So it will cancel this boundary condition. When you go to the other boundary, then other two terms cancel. So boundary conditions for this u tilde of t0 will equal to u tilde of tl will equal to 0. The equation has the following form. So since sorry, I forgot to write the equation itself. U pt minus uxx equals to 0. So when I substitute this u in terms of u tilde, then u tilde tt minus u tilde xx will equal to u tt minus uxx minus second derivative of this term in time minus second derivative of this term So, and do we have anything else in this equation? What can be other terms? Mm. Yes. Oh, the question is, these two terms came from time derivative, but we also had x derivative. Do we need to write anything coming from that or not? Yes, true. Yes. So, uh, our equation has this form. So, u tilde t minus u tilde xx equals to minus x over L u r prime of t minus 1 minus x over L u L primes of t. So, and if you know how to solve this equation with the right-hand side in any form, then we can solve this equation. Uh, so this was the first approach. But the second approach that works, I think, only for this situation on a half line is again just to guess the solution. By the way, the physical picture for this boundary condition is the following. So we have a string fixed at two boundaries, and these boundaries move according to these boundary conditions. So this coordinate of this boundary is ul of t, and the coordinate of this boundary is u r of t. So we are kind of waving this string, and this introduces waves that move between these boundaries. So, mm, so let us consider this second situation. So here again some boundary conditions, but maybe let us say that these boundary conditions are zero, because this problem can always be decomposed into two independent problems. Mm. And here we have some UL of t. So first of all, this UL of t is defined only for t greater than 0. And if you want to extend this to negative keys, we can do it in any possible way. So as we remember, solution to the wave equation ut minus uxx equals to 0 is a combination of two functions. So we have this formula. And by the way, concerning the definition of this UL of t, uh, uh, mm, let us extend it by 0. So let us say that UL of t is 0 for t negative. So the general solution of the wave equation equals to this. Can you immediately guess how to write a solution of this problem? How to guess it immediately? No, it's even easier. So it is kind of similar to reflection trick, but mm, uh, uh, reflected part is not identical to the observable line. So the idea is the following: we can introduce a wave that moves along the real line from negative direction and enters the observable part of this line the moment t equals to 0. And then the boundary condition will coincide with the value of this function as it passes through 0. So can you turn this speculation into some explicit formula? Mm. But in this case, you will have a non-trivial value for either u or ut. So they should both be 0 for t equals to 0. Mm. But they cannot cancel at the same time. In a sense, mm, uh, mm, and both of these functions will be visible for x greater than 0, because in one case they cancel each other, but when we take, for example, if u equals to 0, then these two functions cancel each other uh, yeah, but when we take derivative, then uh, it it will flip signs. In a sense, if a function of minus x cancels a function g of x, then uh, minus x derivative of this function will not cancel x derivative of this function. So it will not work that easily. Oh, probably let me just write the answer, and you'll see immediately that this answer actually works. So, I propose the following formula. And let's see how it works. So first of all, it's a solution of our equation. Mm, uh, Second, if you substitute t equals to 0, it is precisely what we want, right? And third, if you put t equals to 0, equals to u L of minus x, and u t of 0 and x equals to u L prime of minus x. X is positive. So when we look at this requirement, then we immediately realize that both of them equal to 0. Right? So the picture I was talking about is the following. So there is a real line, and there is a function u L of minus x. And this function moves into the positive real line. So it starts moving, and as it moves, we see a picture like this. So. So I probably did not draw a precise copy of that function. The idea is the following. So it moves in, and we see the value u L of t at this point. So, in principle, so I said that it probably does not work that easily in the right case, but actually it can probably be transformed into a solution. to this problem as well, because you see that local description of this phenomena is the same. We see this incoming waves described by boundary conditions, and the only phenomenon we should describe is their reflection from boundaries. So probably if we think for some time, we can also write something like this in the right case. And maybe it's too much for these methods because they work only for the wave equation in 1+1. All other solutions are not that explicit. Well, almost all other solutions. Okay, so are there any questions about this? Yeah. Okay, so now let's switch to the set of new topics. Mm. Uh, So there are several ideas for solutions of PDEs. So the first idea was just solve it.
Is the second idea similar to pointer-arrays analysis of ODEs, or you study them geometrically?
What do you mean by Poincare analysis?
Like in Strogat's textbook, you look at an ODE, but you don't solve it, but you look at fixed points and do analysis. Do we have something for PDEs? So like in
I
a
don't
first
know.
order differential equation, we say the time is x dot equals some function of x, and then you can study the zeros of x and their stability.
I would say, so if you're looking for such cases, then I would say that the only similar problem for coordinate independent linear PD would be to find yes, to study stability of its solution or low positiveness, and if this PD is nonlinear or coordinate dependent, then we can solve non-trivial problems about this smallest eigenvalue, asking whether it is positive or negative, and then whether solution is stable or unstable. So the only analog. But we will not study this. I'm talking about not about this qualitative analysis, but about actual solution of these equations, about some approaches that produce explicit formulas.
When Fourier-based derivatives are just downward.
Yes, it's so there are second and third idea. So this is what I wanted to tell. Yes, so the first approach is like this: find some methods to solve the APD. Like here, it was sufficient just to integrate the right-hand side or initial condition. It was just some calculus, and these ideas also extend to to another equation uh, with a plus sign. But it's less trivial, and we'll come back to this later. But this, but everything, this works mostly for these two equations. So, another idea is to study the object called a green function, which I'll explain a bit later. And the last idea is to use a Fourier transform. So let me explain uh, uh, what green function is. So let us remember how we solved this equation. With initial conditions like u of 0 and x equals to u t of 0 and x equals to 0. So there was the following picture that we have some point x and t, tx, and to get the solution to this equation, we had to integrate a function f of t and x over this domain. So maybe over this domain. Uh, and divide by 2. So, the solution to this equation was written like this. dt prime integral dx prime. So f of prime x prime. So who remembers domains of this integration? Or who can I cover them from this picture? Mm-hmm. Mm-hmm. Yes, and yes, like this. Mm. And the general form of such a formula should look in the following way. So, so it was in 1 plus 1 dimension. And the formula we can expect in the general case is the following. If it is 1 plus b, then we expect a formula like this. U of t and x should be the integral over r d plus 1 d t d dx dx prime times a function g of t x t prime x prime times f of t x prime. So and this function is called the Green function. So in our particular case, explicit formula for this Green function can be read from this integral g of tx prime x prime equals uh, uh, to what? First, to Heaviside theta of t minus t prime. So Heaviside theta of x is a step function defined in the following way. 1, 0, and its value at 0 actually is not defined, but if you want to define it, it should be 1/2. So it can be chosen to equal 1/2, but it's not necessary. So it's a useful function to describe other discontinuous functions. So this gain function for this equation equals to Heaviside theta of t minus t prime. We can actually multiply it by Heaviside theta of t prime, but it's not necessary. Yeah. And then also 1/2, and then by Heaviside theta of x minus x prime plus t minus t prime minus Heaviside theta of x minus x prime minus t minus t prime. So I might make a mistake here, but you can check that this function actually describes that integral in the sense that it equals to 1 in this domain and equals to 0 everywhere else. Mm. So far, it was simply an observation that this solution of the wave equation can be written in the following way using the Green function. And let us let us try to understand its kind of mathematical or physical meaning. So. So let us consider some simple generalization of PD, which we actually derived at the very beginning. So we were studying a discrete analog of a string. It consisted of a finite number of point masses which were connected by several strands. So it was described by still by the wave equation, but with discrete derivative instead of continuous one. So of ut of t and x was ut of so it was u of t x plus 1 minus 2 u t u of t x plus u of t x minus 1. So and we could also apply an external force here. So you could apply some f of x to each of this point mass. So we can add plus f of x. So let me think about signs. Yeah, probably Yes, it should be fine. So we have equation of this form, and also we can add some boundary condition. For example, we can close this string or this discrete analog of a string, and say that there are only n sides. So this is side n. So in principle, we have this kind of equation minus discrete Laplace operator acting on u equals to f. And if we can perform further simplification, and actually let us let us also slightly complicate this problem. You'll see later why by adding some spring that would return this point masses to zero position. So let us add these springs. So which means minus alpha uh, minus alpha u of t and x plus f of x. So in this equation it will give a minus alpha u equals to f. So it's a discrete generalization of this wave, well, in this case, Klein-Gordon equation. And to make it really simple, we can neglect time dependence of u. Or in other words, we can study a stationary problem. Which corresponds to simply a static problem about equilibrium of this system. Point masses, so masses are actually essential, just points connected um, by a strand with unit tension and connected by connected to some fixed points by springs. So and we have to find an equilibrium of this system. So after all, this problem looks the following way. Let me think about all these signs. Probably it is. Yeah, that should be fine. Uh, so let me first say that u of t and x equals to simply u of x, and our original equation has the form uh, minus Laplacian of u of x minus alpha u of x equals to f of x. When x is from 0 to n, it is just a point in a finite set. And n plus 1 is identified with 1. So
Sorry, but in this discrete situation, the Laplace the Laplace is just was written over this line.
yes, yeah. So I'm not specifying it, but yes, it is essentially this. So we need to solve an equation of this type. Right. U of x plus 1 minus 2 u of x. So let me think again about signs. Mm, probably it's fine. Oh, minus u of x minus 1. Oh, sorry, it's not very essential, but still think that I missed one of the signs in this equation. Mm, or maybe it's okay. Mm, Yes, precisely. I made this mistake when I moved this term to the left-hand side. If I fix it, it should be fine. Sorry. Mm. And yes, and this Laplacian is with minus signs, so it should be minus u plus 2 minus u, like this. So plus alpha u of x equals to f of x. So we have such an equation, which is just an equation for uh, for n not even functions for n numbers, and this equation can be written in the matrix form. So we can write essentially that uh, u of x can be packed into a vector. So you can write that vector u equals to uh, u of 1, u of 2, and so on, u of n. And in the same way, f of x can be packed into the same vector, f of 1, and so on, f of n. So this equation can be written in the following way. There is a matrix acting on vector u and gives vector f. And this matrix has the following form. So here we have 2 on the diagonal, 2 plus alpha. And what are other elements of this matrix?
Minus one
Mm-hmm.
on the off diagonals.
Yes, thanks. And what else? Yes, it's true. So these elements are 0, but there is also a minus 1. So there are two minus 1s in the corners because there are shifts by plus 1 and minus 1, which, when applied to point number n, transform it to point number 1. So there is minus 1 and minus 1. So this matrix written here is equal to a kind of matrix representation of the operator alpha minus Laplacian. So this matrix is mm, alpha minus Laplacian. Hmm?
Sorry,
Hmm?
but on the first column, last column, first line, and last line, they are all minus one except, or they are zero.
Oh, there are three diagonals here. 2 plus alpha minus 1 minus 1. So That's all. Then there are triangles that consist of zeros and 1 minus 1 in the corner. So and we all know how to solve such systems.
Math was always that easy.
Hmm?
If math was always that easy,
Ah,
just get a matrix and write it.
but uh, oh, in general, it is that easy in all situations because this idea coming from finite dimensional systems is essentially generalized to PDEs. uh, More or less in the same way. So there are some equations about convergence, existence, low poisonous, and so on. But uh, in a good situation, it always works similar to this. So. Uh, so we simply invert this matrix. U equals to uh, alpha minus Laplacian inverse acting on F. So, and this is essentially what we can call green function for the finite dimensional system. So, and why can we call it this way? Because let us see how this formula is written. So matrix elements of this inverse operator, we can write it like this. We can write it as G acting on F. So G is 1 over alpha minus Laplacian. So So since since matrix indices, vector indices of U and of F corresponded to points on a circle, so we can also draw a picture for this. So there are endpoints placed on a circle, 1, n. So matrix elements of G are functions of 2 points on a circle. So they can be written as G of x and y. In a sense, uh, matrix G is written as G of 1, 1, G of 1, 2, g of 2, 1, g of 2, 2, and so on. And if we write this formula for matrix product explicitly in coordinates, mm, then it looks the following way. U of x equals to sum over x prime from 1 to n g of x prime times f x prime. And this formula should be compared with this formula. So uh, x prime from this problem corresponds to t prime x prime from this problem, to vector x prime. Sum corresponds to integral, and Green function corresponds to Green function. So g of x prime corresponds to the Green function. Okay, so probably we can make a short break here, like 5 minutes or more. Do you have any questions about this? Or, yes. Okay, we were studying this analogy between between discrete and continuous gain function, but let us try to add one more. One more example of such an analogy, which will not really exist. So let us ask the following question. So, what is the equation satisfied by the Green function itself? Uh,
I think it
so,
has something to do
hmm?
with
Yes, yes. So I want to explain it. So where can I write this? Oh, probably I can erase this. So here it's pretty easy. We are just looking for the inverse matrix. So the equation should be mm, alpha minus Gaussian a matrix product uh, with G should equal to uh, to identity matrix. Or in other words, uh, it is the same as to say that alpha minus Laplacian uh, acting on G, uh, if you take matrix elements x and x prime, equal to delta chronica of x, comma x prime. Uh,
Don't we have to integrate it over the domain?
but what do you mean by integrate?
I thought you have to integrate the Green's function against the operator to over the domain.
But it's finite dimensional case. What?
I'm just sorry, I know it from like quantum field theory and stuff, so that's
But in this case, G is a finite dimensional matrix.
okay.
So we simply need to write what this product means.
Oh, sorry, I was talking about the continuum case.
Yeah, but also in the continuum case, it will be the same because this is a differential. In this case, a difference operator that acts on a given function. So it is simple. Oh, delta Kronecker uh, is 1 when x equals to x prime, and is 0 otherwise. So there is this uh, equation, and if I write it explicitly, then it looks like this. We write the action of this difference operator on a function of two variables in the first variable. So um, uh, it writes like g of x plus 1 x prime uh, minus plus alpha plus 2 g of x prime minus g of x minus 1 x prime uh, equals to delta of x prime. So Green function is a specific solution of the original equation with the right hand side given by delta Kronecker. So we see that that this difference equation is written in the variable x. So I can use the red color to reflect this fact. So there is variable x, and all operators act on this variable. So So with this specific right-hand side. So this vector f equals to 0, 0, 1, 0, 0. So this position is x prime. Or we can draw it. We can draw a plot for this function like this. We have a circle with many points, and this right-hand side equals to 0 everywhere except point x prime where it equals to 1. So there is a kind of a unit bump at point x prime. And uh, interpretation of this formula of a solution in terms of a Green function is the following. Mm. So let us again use a different color for x.
I don't understand why, that's the part where you put all the zeros in the vector f, the function.
Because this is the right-hand side of our equation. It is considered as a function of x, so it equals to 0 for all x's except x prime. X prime is a parameter in the right-hand side. So let us look at this formula. Uh, uh, the only x dependence here comes from the Green function. Uh, so we can say that we can perform a trivial expansion of arbitrary right-hand side over this delta chronicas. So first, have a trivial remark that f of x, let's again use a different color, f of x equals to sum over from x prime equals to 1 to n delta conic of x and x prime f of x prime. So as a function of x, f of x can be written as a linear combination of such functions that equal to 1 at point x prime and equal to 0 everywhere else. And these functions, these elementary functions, should be taken with coefficients f of x prime. So in this way, we reconstruct our original f of x. So we simply take a combination of n such functions with appropriate coefficients. And so it was in the first remark, and the second remark is that we can use linearity of our equation. So we know that alpha minus Laplacian that acts in the first variable on a function g of x prime uh, equals to delta Kronecker of x and x prime. Uh, Then, if we take a linear combination of these statements, then we can write that maybe on this line alpha minus Laplacian in x sum from x prime from 1 to n g of x prime f of x prime equals to sum of so, and what is this in the right hand side? Hmm? Yes. So, are there any questions about this, or is it completely clear or unclear?
What property are you trying to show about the Green's function of this discretization?
So, first of all, I wanted to show that Green's function solves the same equation as before, but with a simpler right-hand side.
It's like
So.
a dual equation.
No, it's just the original equation, but with f of x specified to this specific function. So it uh, so it is simpler, and and there are different methods to find this green function. Um, and so some of them work equally well for such equation, for equation with an arbitrary right-hand side, but some approaches are easier to apply with the specific right-hand side. Ah, by the way, one remark uh, is the following, that mm, in this equation, It also has a continuous analog. Mm, So in this case, it will be dt squared minus Laplacian g of x uh, tx t prime x prime. It will equal to all so-called delta functions. So they are called delta functions. They are examples of generalized functions. So in order to solve this natural generalization of the equation for green function, we will need to introduce generalized functions. Uh, yeah, so. mm, And by the way, so I'll tell this a little bit later, but in this particular case, this equation can be solved explicitly. So in principle, both equations can be solved, but this one is much easier. So, so it's easier than generic right hand side. Hmm. So are there any questions so far? Because I actually don't tell anything new. I've just formulated some statements from linear algebra in a slightly different manner to show the analogy with the continuous case. Uh, so let me probably erase this. So now let me discuss the following question. How to compute the green function? Well, there are two possible answers. One is just to solve the equation. And it's a little bit similar to the first approach to PDEs, and they mostly work uh, in the same situations. But another approach is a little a little bit trickier. Namely, we can use the Fourier transform. And now it's time to tell what the Fourier transform is. Uh, so let us look at our system. We clearly see that it has a symmetry, and namely rotational symmetry. So, mm, uh, so f of x f of x goes to f of x plus 1. Or in this matrix notation, this can be written as uh, vector f goes to vector tf, where t is a shift operator. Which is written explicitly uh, as mm, so. Tell me what matrix should we write here to get this mapping? What should we write the diagonal? Yes. Yeah, thanks. So this matrix looks like this. 1, 0, and 1 here. So everything else is 0. And here as well. There are non-trivial values. Uh, so matrix T has this form is 0, 1, 1, 1. And what is T inverse? Yes, thanks. Uh, so, and if you look at our equation, then we realize that this operator can be written as this operator alpha minus Laplacian can be written as uh, uh, 2 plus alpha times identity operator times identity operator minus t minus t inverse. So our problem is to compute the inverse matrix for this matrix. And it is always easier to compute the inverse matrix if you use the basis for eigenfunctions or eigenbasis. And we can do this here. And the problem of finding the eigenbasis is even simpler than diagonalization of this complicated original matrix, because it can be expressed in terms of a simple translation matrix. So let me erase this. Uh, So if we diagonalize T, then this matrix becomes diagonal as well. So to diagonalize T, we need to solve its to solve the eigenvalue equation, eigenvalue eigenvector equation. Or in other words, f of x plus 1, maybe let us use uh, some number, some notation here, phi k lambda k.
I thought if we diagonalize t, we change the basis, so we have to change the form of alpha. I'm sorry, the discrete Laplacian.
What do you mean? So if I write it in defined basis, then of course it will be defined. What is the statement?
Oh. But shouldn't you note that that's Laplacian in like another basis?
Hmm?
Like
Well, I'm not specifying what precisely is happening. I'm just thinking about matrices. So, what is the solution of this equation? Uh, Let me write so phi k. Who knows how to solve this? Mhm. Not yet. So it's true, but first I'm asking how to solve this equation. So it's like this, right? Yeah, and to make this defined on a circle, we actually need to ask lambda k to power n to be 1. So phi k of x equals to e to the 2 phi I k x over n. And I can also normalize it by 1 over square root of n, but we'll discuss it later. So this is the Fourier basis for, for this equation. So it's a nice basis of functions to study these operators.
It required that we had the periodic symmetry though.
Yes, but we are studying precisely this case, this periodic symmetry. Yes. So, do you have any questions?
We divide by root of n, like some sense to the rise.
Yes. So far it doesn't matter because mm, our functions are defined up to the overall factor, but we can introduce this notation from the very beginning. So, okay. So thanks for your attention. See you tomorrow.
Are you guys taking the field theory course?